Welcome to today's seminar. Today's speaker is Mike Tait, and he will be speaking about 4 conjectures in extremal spectral graph theory.
Thank you very much. Yeah, so thank you all for coming. I want to tell you about 4 conjectures in extremal spectral graph theory. So let me tell you what that is in a moment. But first, let me say that this is all joint work with Josh Tobin. So Josh is a 5th-year PhD student at UC San Diego, and this is all work that we did sort of in my last year at UC San Diego. Josh did a good guy. So I think some of you know, right? Yeah.
This is thesis work?
I think sort of this will probably make up most of what's in his thesis. That's right. Okay, so the questions. Okay, so my research always starts from extremal graph theory. So let me say what that is. Extremal graph theory. The questions ask you to optimize a graph invariant over a family of graphs. So this is a very broad question, and it's meant to be that way. So you can sort of ask lots of different questions. Maybe the most well-studied extremal graph theory question is a Turan type question. So this notation means what is the maximum number of edges in an n-vertex graph that has no h as a subgraph. So here, the graph invariant that you're asking to optimize is the number of edges, and the family of graphs you're asking to optimize over is the family of graphs that have no h as a subgraph. Right? Like the four-color theorem is a very famous extremal graph theory question. You're trying to maximize the chromatic number, so the chromatic number is your graph invariant. The family of graphs is planar graphs. Okay? But you can ask sort of any question that you want along these lines. So you can take your favorite graph invariant, whatever it is. You can take your favorite family of graphs, and you can say what graph in that family of graphs, or which graphs maximize this graph invariant. So there's 2 questions: is what is the maximum value, and what is the extremal example? Okay. On the other hand, spectral graph theory, the goal is to associate a matrix with the graph, and then from the eigenvectors and eigenvalues of that matrix to do some structural properties of the graph. So there are lots of different matrices that you can associate with the graph. For this talk, I'm always going to be interested in the adjacency matrix of the graph. So should I say what the adjacency matrix of the graph is? Everybody's good with that? Okay, so we're going to work with the adjacency matrix. And this sort of spectral graph theory also has a very long history of study. Thousands of papers have been written on spectral graph theory. Lots of people here are interested in it. And yeah, I don't need to go through a history, but these kind of last 3 are similar to the last slide, because the point I want to make is just that spectral graph theory and extremal graph theory heavily overlap each other. So you can ask similar and related questions to the previous slide. And so this kind of intersection is what I'm interested in. So that's what I mean when I say extremal spectral graph theory. I mean extremal graph theory problems where the graph invariant is spectral in nature. And I'll talk about why you can sort of recover some classical extremal graph theory problems. So this sort of intersection also has a very long history of study. Just this subset of extremal graph theory, or you can think of it as just this subset of spectral graph theory, has many papers have been written about this. This is just a small selection of them. Stanley's bound maximizes the spectral radius of the adjacency matrix over graphs with m edges and characterizes the case of equality. And then you can sort of, the first questions asked in Turan type theory were how many edges can be in a graph with no complete graph as a subgraph. So this goes back to Mantel's theorem, and then Turan's theorem. And then how many edges can be in a graph that has no KST as a subgraph. And so these questions, well, this one has been solved, this one has not been solved, but you can ask kind of the corresponding question for spectral graph theory. So if I have a graph with no KR plus 1 as a subgraph, what is its maximum spectral radius? And kind of, if you can say something, maybe I'll write it here, it's well known that if, okay, lambda 1 is, maybe get that on marker here.
Try some lines on
Okay, so I'm just going to write lambda is lambda 1 of the adjacency matrix of a graph G. So this is the maximum eigenvalue. So it's well known, and I'll say why in a minute if you don't know this, that the spectral radius of the adjacency matrix is less than or equal to the maximum degree of the graph and bigger than or equal to the average degree of the graph. So this is twice the number of edges over n. And I'll say why this is in a moment. But this is sort of one of the first facts you learn in spectral graph theory. And this can tell you something about the classical Turan type problem, right? If I say that a graph with no kr plus 1 as a subgraph has an upper bound on the spectral radius, it also gives an upper bound on the average degree, which is exactly what these Turan type problems are asking. And so,
The lambda with the line over it, is that average?
oh, sorry, this is a D. D with a line over it, yes.
D.
This is average degree. Yes. Okay, so this is one of the motivations for studying these extremal spectral graph theory problems is you can often recover classical extremal graph theory theorems. So, for example, Nikiforov proved a strengthening of Turan's theorem. It says if the spectral radius of your graph is bigger than the spectral radius of a Turan graph, then you contain a kr plus 1. This improves Turan's theorem. It's stronger. Nikiforov and also Latsi Babai and his PhD student Guiduli proved a spectral version of the Kurvari-Shosht-Turan theorem. So this improves the classical Kurvari-Shosht-Turan theorem. So that's one of these motivations. But there have also been there's also been lots of other study on sort of other spectral extremal graph theory problems. So they're kind of, I think they're interesting by themselves, but maybe this is one motivation is to try to recover things. Yes.
Kurvari-Shosht is Zerenkevich?
Yeah, so Kurvari-Shosht-Turan is the best upper bound for the Zerenkevich problem, yes. Yeah.
So this is Zerenkevich is a different one than the crossing number stuff.
Yes, this is the maximum in a kind of a bipartite graph, the maximum number of edges with no KSD as a subgraph, or you can formulate it in terms of matrices if you want. Okay, so, yes. Okay, so I want to tell you the kind of the conjectures that we were interested in this spectral extremal graph theory. I've grouped them into pairs of two because each pair is related to each other. So the first one is a conjecture of Boots and Royal, and also independently Cow and Vince in 1993. And they conjectured that the planar graph of maximum spectral radius is the join of P2 and Pn minus 2. So I'll show you a picture in a minute. And the second conjecture is very similar. The outer planar graph of maximum spectral radius is the join of P1 and Pn minus 1. So these both are related to geography for some reason. So I don't know why, but I guess what other papers have said in their introductions is that geographers were related to studying connectivity of a network, of a geographical network, and for some reason the spectral radius, they wanted a theoretical upper bound on this spectral radius, so they were interested in this. The second two conjectures are also related to each other, and so these two are about sort of the irregularity of a graph. So both of these conjectures are kind of asking what is the most irregular graph with respect to some metric. So the first one is if you have a connected graph and you look at its adjacency matrix, so connected is the same thing as its adjacency matrix being irreducible. So what that means is the Perron-Frobenius theorem says if I have an irreducible matrix, it's going to have non-negative entries because this is an adjacency matrix. Then if I look at its first eigenvector, the first eigenvector is going to have all positive entries. So no zero entries, no negative entries. And so I can look at this first eigenvector, so I can look at this x and sort the entries, right? What is the maximum entry? What is the minimum entry? And then I can look at their ratio, right? So if I look at the ratio, I get this number that's bigger than or equal to 1. And this is called the principal ratio of a graph. So it's also well known. Well, I guess, okay, if you don't know this, you'll learn it in Steve's class next semester. That, okay, let me just use some notation. So A is going to be the adjacency matrix of my graph. AX equals lambda x. So x is an eigenvector, where lambda is the spectral radius. And one way to compute this eigenvalue is as a maximization problem. So this goes by several names, I think, in the literature. But one characterization of lambda is the maximum over all x non-zero of x transpose AX over x transpose x. So this characterization sort of gives you this. If you plug, it gives you this bound on the spectral radius. If you plug in certain vectors for x here. So if I take, for example, z is the all ones vector, this says lambda is bigger than or equal to z transpose az over z transpose z. If you sort of do the matrix multiplication out, this is twice the number of edges in the graph over n, which is the average degree. Okay, so I have this lower bound on the spectral radius. The spectral radius is bigger than or equal to the average degree. You can also check using this thing that this equality is attained here if and only if the all ones vector is the eigenvector here. And that means if the all ones vector is actually the eigenvector here, this implies that the graph is regular. So the spectral radius, okay, so actually how should I phrase it, is that the graph is regular if and only if the all ones vector is the principal eigenvector for the adjacency matrix. So what this means is that if I look at this principal ratio, I can rephrase this as saying that this principal ratio is equal to 1 if and only if the graph is regular. So this quantity is bigger than or equal to 1. If it's bigger than 1, the graph is irregular. So how much bigger than 1 this is measures how irregular the graph is. Right? And similar here, and using exactly the same thing that I wrote on the board, this spectral radius minus the average degree, what I wrote on the board said this is bigger than or equal to 0, right? You can also kind of look at this characterization and show that the spectral radius, the only way that the spectral radius can equal the average degree is if the graph is regular, right? So if the graph is regular, these two things get sandwiched together, and the spectral radius equals the average degree. And this is a necessary and sufficient condition. So the spectral radius is equal to the average degree if and only if the graph is regular. So this quantity is greater than or equal to 0 with equality if and only if the graph is regular. So how large this quantity is measures somehow irregularity of a graph. So both of these conjectures are measuring how irregular my graph is. So I'm kind of maximizing this thing. Yeah.
So it strikes me that maybe gamma isn't quite the easiest thing to compute because it's really very discrete. Maybe something like the 2 norm over the 1 norm or something like that might be something that would measure it, and maybe it would be a little bit easier to handle.
Yeah, so so there's actually, so this is kind of how this project actually got started. So the project first got started at GRWC 2014. I can tell you this history. So Josh Tobin submitted an open question of Erdish for a problem, which I guess is why it didn't get selected. And we tried to work on it for a long time. We still haven't solved it. This is one of the problems I would most like to solve. So it's like something about counting walks in graphs. If you're interested, I can tell you about it. But somehow, the conjecture is to prove some inequality that it's an equality if the graph is regular. So somehow it seems that this quantity also measures graph irregularity. And this led us to this whole study of graph irregularity. And there are probably 10 different ways to measure. None of them are comparable to each other, and none of them seem to be completely right, I guess. All of them sort of have their downsides and upsides. So, yeah, I think because what does it mean? The graph is very irregular, right? It's not clear what it means. Okay.
So conjecture 4, where it says it's a pineapple graph, is that any pineapple graph or a specific pineapple graph?
Okay, so if you have a pineapple graph, so let me just show you what a pineapple graph is. It's a cleat that has leaves joined to one vertex. That's what a pineapple graph is. This graph, you can kind of make an equitable partition here with 3 classes, and so you can compute the eigenvalues directly, and yeah, so the spectral radius is the solution to a cubic polynomial. So you can kind of optimize over what it is. And the optimum is easy to compute. So basically the optimum is something like when this is n over 2, approximately. Okay, so our theorems are that the conjectures are true for n large enough. Large enough means, for these first 2, it means something like between about 10,000 or so. And for these 2, it means something like 100,000 or maybe 1 million. So definitely too much to do by computer. It's maybe possible that we could optimize all of our proofs in this one and then do an extensive search that utilizes like all of the stuff in the proof that shows what the structure looks like. But it's not even clear that you could do that, and it seems like it would be a lot of work. So, and definitely these we can't optimize enough to do by computer. And we use this n large enough very many times in the proof. So. I kind of think, yeah, there's no hope of sort of doing this for all n unless you do something different. And I'll just note that Leslie asked right before the talk about this one. This conjecture is not true when n is 8 or 9 or 7 or 8 or something like that. So there, you kind of at some point need n larger than 9 for this one. So, okay, so let me just do some. Okay, so let me say something about the proof, and then I'll do some preliminaries, and then I'll get into it. So. These theorems are kind of different, but if you zoom out from the proof, they all kind of look similar. The details are different, but kind of the rough outline is similar. So the idea is that you use your conjectured extremal example to say that whatever invariant I'm interested in has to be at least a certain value. It has to be at least, bigger than some other example. And from this very small amount of information, I deduce some small amount of information about the structure of the graph. So I take a small amount of information about the spectrum, or the eigenvectors, and I use this to deduce a small amount of information about the structure. And now I use this small amount of information I know about the structure and bounce back to the eigenvector and try to say that I can get precise information about the eigenvector. Once I have precise information about the eigenvector, I use that to get more exact information about the structure. So it's really kind of a bouncing back and forth process. In the beginning, I sort of see that maybe my extremal graph looks very roughly like what the conjectured extremal graph is, and then I kind of zoom in more and more and clean up my picture more and more throughout. Get a more and more clear picture, and then eventually, once you're very close to the extremal graph, then I can do an alteration to show that it has to be the extremal graph. So let me just do. Okay, so let me just write some things on the board. So. Okay, so I'm going to do a normalization that turns out to be useful. The normalization is, so x is going to be the leading eigenvector. The normalization is going to be that I'm going to normalize so that the maximum entry in the eigenvector is equal to 1. And I'm going to fix z so that z has eigenvector entry 1. So if there are more than one of these, you can just choose it arbitrarily. And now, I just want to do the eigenvalue equation a few times. So this is a matrix equation, right? What this means is this is a system of equations, right? So this equation means for all vertices in the graph, the sum over v adjacent to u of x sub v equals lambda x sub u. Right, so I'm just doing this a x equals lambda x. So this statement is the youth row times this vector equals the x sub u here. that's what that means. And by the way, I've normalized this. This is less than or equal to the degree of u, because I've normalized so that each term here is less than or equal to 1. There are exactly the number of neighbors terms here, so this is less than or equal to the degree of u. Okay, the second thing I want to do is multiply this whole equation by lambda. Okay, so if I look at lambda squared x of u, this is equal to sum of v adjacent to u, lambda x of v. And now I just want to look at this lambda x of v and apply equation 1 to it. Another way that you can think of this is I'm just writing down the eigenvalue eigenvector equation for a squared. So this is equal to sum v adjacent to u, and now lambda x of v becomes sum w adjacent to v x of w. Okay, and now I just want to do, I want to take this equation and just apply it to the vertex z. So the vertex that I've chosen to have eigenvector entry 1, I'm just going to rewrite this equation. So lambda squared times 1 is equal to the sum v adjacent to z, sum w adjacent to v of x of w. So I haven't done anything yet. Okay, and now I want to do some double counting. But first I'm going to break this double sum into two double sums. So I'm not going to do anything yet. This is just rewriting. So w is adjacent to z. So I'm kind of worried about these vertices that are at the end of a walk of length 2 starting from z. And I'm worried about these eigenvector entries. So I'm just going to break it into two pieces, the ones where these are in the neighborhood of z, and the ones where these are not in the neighborhood of z. So this is just w in the neighborhood of z, x of w, plus sum v adjacent to z, sum w, this should be v here, w adjacent to v, w not in the neighborhood of z, x of w. Okay, and the way I've normalized, again, the same exact way that I upper bounded this by the degree of u, each of these summands is less than or equal to 1, right? So I'm going to do some double counting now. So I'm starting with my vertex z, and I'm looking at walks of length 2, right? So this is v, how I've written it, and this is w. So you can think of each of these as the endpoint of a walk of length 2, or you can count this from kind of the edges that are here. So that's how I'm going to do it. And there are two types of endpoints, right? So there are two types of endpoints. There's endpoints where w is in the neighborhood of z, and there's endpoints where this is z, this is v, and my endpoint is not in the neighborhood of z. And if instead of thinking about counting this in terms of the endpoints, I think of this as counting in terms of the edges, each of these edges can get counted twice. Each of these edges can get counted once. And each of these entries are at most 1. So this becomes less than or equal to twice the number of edges in the neighborhood of z, plus the number of edges in the neighborhood of z, with one endpoint in the neighborhood and one endpoint not in the neighborhood. So it's twice the number of edges within the neighborhood of z, plus the number of edges between the neighborhood of z and its complement. So let me just have this on the slide.
Neighborhood, we're not counting z.
We're not counting z, right? So yeah, some of these walks look like this, right? There's kind of 3 types of walks. There's one that looks like this, there's one that looks like this, and there's one that looks like this. Right? So these are going to get counted in this piece. Right? Something like this can only get counted once per edge. And something amazing has happened here. So I haven't done anything yet. I've had no original thoughts. All I've done is normalize the eigenvector in a useful way and written down the eigenvalue equation for a squared, right? But this gives a one-line proof of Mantel's theorem, for example. How, right? Okay, what does this say? Lambda squared is less than or equal to twice the number of edges in the neighborhood of z plus the number of edges between. What does Mantel's theorem say? It says if G is a triangle-free graph, G has at most n squared over 4 edges. If G is a triangle-free graph, there are no edges in the neighborhood of z. So this says lambda squared less than or equal to a cut in the graph. So the number of edges between the neighborhood of z and its complement is at most the maximum size of a bipartite graph in a graph on n vertices, right? This actually says something stronger than Mantel's theorem, right? This says the average degree is less than or equal to the square root of the max cut in the graph in any triangle-free graph, right? And you can prove several other theorems in one line just using this normalization. So Hervari-Chauche-Turan for s equal to 2 you can prove. You can prove Stanley's bound for the leading eigenvector. You can prove there are at least five papers that kind of do variants of Stanley's bound when your graph is triangle-free, when your graph is in other cases. It proves all of these things. Yeah, it's an amazing thing. I haven't done anything, right? Just normalization. So something magic just happened. I'm not sure what it is. But okay, so we're going to kind of okay, so how do we prove this? These things. So in this, okay, how am I doing? I have until 3, is that right? Or
No.
Okay, so I sort of want to show you the proofs of, or the steps to the proof of this one. This is the easiest one. This proof is only 2 pages long, so I want to sort of show you most of the steps and then tell you the corresponding steps in the other one. So I'll show you the proofs of the second one and the steps of the other ones. So our broad outline was to get use the conjectured extremal example to get rough spectral information on my graph. So let me say here I'm going to have G as outer planar, and actually what this means is that G has no K23, G has no K4 minor, and the number of edges in G is less than or equal to 2n. I think that's all we use. And our goal is to show that G looks like this. G has maximum spectral radius. I'm assuming G is my extremal example. So our goal is to show that G looks like this. And the first step is this graph, K1 n minus 1, is outer planar. And lambda 1 of K1 n minus 1 is equal to square root of n minus 1. So lambda 1 of G has to be bigger than or equal to this, right? Okay, so this is easy. So I know something rough about my lambda 1, right? Okay, so now I use this rough spectral information to deduce rough structural information. So that rough structural information is that I have a vertex of large degree. So this is, I'm going to write, this is our goal, this is what we know currently. So this is my vertex Z. Okay, I'll add to this picture in a second. So how do I show that there's a vertex of large degree? I prove this lemma, and if you look at the lemma, this is a lemma that's true for all vertices in the graph. If I plug in my vertex Z here that has eigenvector entry 1, this says that the degree of Z is bigger than n minus something very small. So really it's adjacent to almost everything in the graph. And how do I do this? Okay, So how do I do this? So I do this exact same thing that I did before. This setup, lambda 1 squared x sub u is equal to the sum. I want to write the same notation, right? Y adjacent to u, sum of v adjacent to y, x sub v. So again, this is just the eigenvector-eigenvalue equation for a squared. And now I do this double counting. So these are the types of walks that Alex asked about. Was there's one special type of walk where I can go up to y, and then v is going to be the same vertex as z. And so this is just less than or equal to, how many times can that happen, the degree of z? Each entry is less than or equal to 1, and then plus this same sum. Y adjacent to u, v adjacent to y, x of z.
du.
Yes, du, thank you. So I should make this a u. Yes. Very good. And now, okay, so what's happening here? I have a vertex u, I have a walk that goes through y and then goes to v, right? How many times can this happen for each vertex v? So how many y's can there be is what I'm asking. Well, I claim that there can only be 2 of them, because if there were a third one, this is a k23, right? So my graph is outer planar, it has no k23, so there can be at most 2 of these. So this is less than or equal to the degree of u plus sum over y now to x sub y. Okay, and now, again, I just want to use, this was, I think, the second equation that I wrote on the board. So instead of bounding from x sub y, I'm just going to bound by the degree divided by lambda 1, right? So this is less than or equal to the degree of u. The eigenvector-eigenvalue equation says that for any u, x sub u is less than or equal to the degree of u over lambda 1. So that was the first equation I wrote on the board. So now this is a bound in terms of the number of, okay, let me just write this as sum y dy over lambda 1. And now this sum is a sum over the degrees of vertices in my graph. So this is bounded by twice the number of edges in the graph. The number of edges in the graph is at most 2n. And so I get a bound that looks like this. And you can look at this as so this is a lower bound on the degree in terms of something that I wanted to lower bound this degree in terms of the eigenvector entry, but it's a lower bound on the degree also in terms of the first eigenvalue. And so now you can do calculus and say that this lower bound is increasing in the first eigenvalue. So this lower bound on the degree is an increasing function of lambda 1. And so we already know that we have a lower bound on lambda 1, is what I'm trying to say. So lambda 1 is at least square root n minus 1. So I can plug in square root of n minus 1 here and have a lower bound on my degree. Okay, so this is how we prove this lemma. And that means that in my picture, I have my neighborhood of z. I have possibly some other vertices here, but this has size less than a big constant times square root n. So really this vertex is already adjacent to most of the graph. So we're sort of almost looking like this already. So for the other for the other 3 conjectures, for this one I showed there are 2 vertices of large degree. The proof is similar, but it takes longer. For this one we show that if your principal ratio is really going to be close to n to the n, you have to have a diameter that's very close to n, basically. And for this one, we show that if lambda 1 minus the average degree is going to be asymptotic, or is going to be at least n over 4, then the average degree has to be asymptotic to n over 4, and lambda 1 has to be asymptotic to n over 2. Okay, so now we use this to show that the other entries are small. So let me just write the lemma that I had before. So the lemma said that for all u, what did it say actually? Let's see. The degree of u is bigger than n times the eigenvector entry for u minus a constant times root n. Okay, so how do we use this to show that besides this vertex z that has eigenvector entry 1, the other ones are small? So now my kind of eigenvector eigenvalue thing looks like this. Okay, so I have this one vertex z of 1, and now what I'm saying is the rest have entry less than c root n. Okay, so if I look at my vertex u, this is not equal to z, and I look at my vertex z, z is adjacent to almost the whole graph, besides these 11 root n entries, right? So this vertex u, it could be adjacent to all of these 11 root n vertices, but it's adjacent to at most 2 neighbors in the neighborhood of z, otherwise I have a k23. So the degree of u is less than 11 root n plus 2. Okay? And, okay, this is, we're already done, right? This is, I move this to this side, n times the eigenvector entry for u is less than a constant times root n. And I just divide by n. Okay, so this looks good to me. So, yeah, so, okay, for the other ones, what do? I show that same thing for the planar case. If you kind of, even the details are very similar for these two, but it's just more technical in this case. So the proofs are very similar. For this one, I show that I have what's called a pendant path. So a pendant path is, I know that I have this diameter that's very big, but it might have some, some part of the graph on each side of it. A pendant path means there's only, the rest of the graph is all on one side. So there's a path kind of hanging off here, there's nothing on the other side here. And my goal in this whole thing was to kind of go from spectral information to structural information back and forth. So I did spectral information, structural information. Here, this is definitely spectral information. I'm saying something very precise about the eigenvector entries. Here, I claim that this is also spectral information. Because if I have a pendant path that I know is actually almost the whole graph. If I have a pendant path like this, I can write down a recursion for the exactly what the eigenvector entries look like, right? I can just use the eigenvector eigenvalue equation over and over, and I can write down exactly what all of these look like. So I really do know what the eigenvector looks like for almost the entire graph at this point. And then for this one, we show the rough structural information we show is that there are kind of about n over 2 vertices, and they all have degree about n over 2. I'm starting to look like my graph. Okay, so my picture hasn't updated, so the structure hasn't updated, I just know something about these eigenvector entries. Okay, so now what I do next is I've gone from knowing that I'm adjacent to almost everything, using that to show that all of the eigenvector entries, I know them very precisely, and now I'm going to use that to show that actually I know the structure very precisely. So I'm going to say that this red set is empty. Okay, so how do I do that? I'm going to assume that there's this y in here, and I'm going to have a contradiction. Okay, I claim that if I sum up, so if I look at, this is my set B. My previous lemma was that every eigenvector entry in here is bounded by a constant over root n. But now what I'm going to claim is actually if I sum up all the entries in here, so V is in B, sum up all the eigenvector entries, this is also bounded by a constant over root n. And since I only have 7 minutes, I'm not going to show you the proof. The proof is exactly the same as the proof that each one was small, but now I use the fact that we already know each one is small. So I do exactly the same proof, but instead of substituting 1, I substitute C over root n. Right? So I won't show you the details, but the key is that when n is large enough, this is smaller than 1. Okay? And now what am I going to do? So I'm going to make a new graph. I'm going to show there's a contradiction by making a new graph. So let me call this G. My graph here is Z. It's adjacent to everything except for possibly this set B. And I have this vertex Y here. So Y has some neighbors, but Y is not adjacent to Z by assumption. So now I'm going to make a new graph. I'll call this G+. it's the same as the old graph, except I delete all of these edges and I make y adjacent to z. Okay? So the first claim is that because I've deleted all of these edges, this graph is still outer planar. All I've done is add a leaf to a graph. Adding a leaf to a graph retains outer planarity. And now I want to use this characterization. So this characterization of the eigenvalue. So the spectral radius of G plus is at least, well, let me write this like this, right? This is the maximum over z not equal to 0, z transpose the adjacency matrix of G plus, z over z transpose z. This is just this eigenvector eigenvalue characterization. So this is bigger than or equal to, if I plug in the eigenvector for G here, I get an inequality, right? Because this is a maximum. So this is bigger than or equal to x transpose A of G plus x over x transpose x. And now I'm just going to subtract lambda 1 of G here and subtract x transpose A of G x over x transpose x. Because lambda 1 of G is equal to this. I'm assuming that x is the eigenvector for lambda 1. And now the adjacency matrix for G plus and the adjacency matrix for G are very similar. So this A plus minus A is a very sparse matrix. I can write down exactly what it is. This 1 comes from this edge that I added here. These subtractions come from these edges that I deleted here. Everything else cancels out. And now I use this claim that this sum is less than 1 for n large enough. So what does that mean? That means lambda 1 of A plus minus lambda 1 of A is strictly positive. This is a contradiction because we're assuming G is an extremal graph. Okay, so really this y can't be here. Otherwise we have a contradiction.
So that z is not your special z.
It is my special z, yes.
Can I just ask if
Yes.
you go back? So you proved that each of the individual xu's had c over square root of n entry.
Yeah.
But you could have potentially...
Root n of them. Yeah, this
Root
is,
n of them.
so I didn't prove this claim.
Okay, all right.
Yeah, so you prove this claim by, you kind of go through the same proof that shows each of these is small. And at some point in that, I use the fact that each was bounded above by 1. And so now I kind of go through a similar proof, but now that I already know that each of them is over c root n, I get kind of this extra factor of root n. It's similar to what I presented, but you definitely have to prove this.
Okay.
Yeah. Okay, good.
And xz, on the previous slide, xz is 1 and z is not related to y, not adjacent to y in that last line. So I'm really confused.
The very last line, you summed over xz, where z is adjacent to y.
Yeah.
But
I think what Leslie's question is, if this z is the xz equal to 1,
That's
I
not
guess
the
it's not.
z.
Sorry, that was your first question.
Yeah.
Yes. No, this is
That's
not my
just a
specialty.
variable.
Yeah.
Okay.
Only
Yeah,
one
sorry,
z.
okay, so that's very poor notation, yes. So I should change this. Okay, good. So, since we have 2 minutes, I should finish, but it's good because the proof is almost done. So, now that my graph looks like this, right? Z is adjacent to everything else in the graph. So I can just look at this neighborhood. I want to show that the neighborhood induces a path. Every other vertex in the graph, we know it's in the neighborhood now, but in the neighborhood, this vertex can have degree at most 2. Otherwise, again, there's a K3. Okay? So if I look at the graph induced by the neighborhood, it has max degree 2. Right? So that means it's a disjoint union of paths and cycles if you have degree 2. If I were to have a cycle here, this is a subdivision of K4. It's a K4 minor. So actually there can be no cycles. So I have a graph that has max degree 2 and has no cycles in it. So what is it? It's just a disjoint union of paths. Okay. So now, my graph is a strict subgraph, or it's possibly strict. If this thing's the whole path, then it's not a strict subgraph. My graph is a subgraph of my conjectured extremal graph. If it's a strict subgraph, I use, again, this characterization of lambda 1 as x transpose ax, and the fact that all of the entries in the eigenvector are positive, and this shows that this graph has spectral radius strictly bigger than this graph. Okay, so all of the other theorems are just as simple to finish. Like once you get very close to the extremal graph, it really is very simple to finish the proof. Okay, so these are some open questions. This one was the one that I came here to work on, and we've been trying to do it, and so we'll see if we can. We haven't been able to finish it yet, so this seems harder than I thought it would be, but we'll see. And then these are some other ones. So this question is related to an old question of Erdős about making a graph bipartite, so maybe solving this would kind of give some steps toward that conjecture. You can kind of ask similar questions for any graph parameter that can be counted by the eigenvalues, basically. And this last one is a question of Steve Kirkland and David Gregory, and I'm not sure if there were other people in the paper, but this question is about 15 or 20 years old, and there are 50 papers that are written on it, but somehow it's very, very far away from being solved. There are 50 papers written on it, but nobody's made any progress. Let me say that. So yeah, that's where I want to stop. You can't see. This is Josh. He's washed out. Thanks.
Questions? Any questions?
So you work with the biggest eigenvalue, but a lot of your questions have to do with the biggest and the smallest, which seems to be like that your methods will have problems.
So our methods will have problems for this one for sure. But for this one, I actually think they won't. So the methods can carry through because the smallest eigenvalue is the minimum over z transpose az over z transpose z.
Sure.
So the reason that we'll have trouble here is because when you do this kind of alteration method, if I'm adding a minimum, I'm going to get a bound going the wrong way. Like the bounds will always be going the wrong way here. But if I'm subtracting here, then using this characterization, the bounds will be going the correct way. So I think the methods can work for this one. Yeah. So it's not clear for the other ones. Like I don't know if our method can work for this one. I'm not really sure about this one.
I have a question that might not be very related to this talk. So the third conjecture talking about which graph is the most irregular, sort of. And so the principal eigenvalue is all positive numbers, and whenever it's evenly distributed, then it is regular.
Mm-hmm.
So does anyone look at the entropy of the principal eigenvalues?
Oh,
something like that, or would that be interesting?
So I have no idea. Actually, I have zero idea. It's a good question.
Thanks.
No more questions. Let's thank Mike again.